All right, welcome back, everyone. Please go ahead and take your seats. Our next speaker is Dr. Emily Pass, who's a Torres Fellow at the Massachusetts Institute for Technology, which I think we're not supposed to say here at Caltech, but she's going to tell us all about the demographics of planets orbiting M dwarfs.
Is this on? Yeah, we're good. Awesome. Yeah, I'm really excited to be here today to talk about one of my favorite topics, M-dwarf planets. But before we dive into the demographic side of things, I wanted to talk a bit about M-dwarfs and what they are and why we care about them and what we need to know in order to appreciate the stellar context their planets reside in. So what is an M-dwarf? The basic definition of an M-dwarf, we're talking about spectral type. So we have our classic OBAFGKM sequence. M dwarfs are the one on the end. They're our coolest members of the spectral sequence. But it's important to remember that this, idea of spectral typing is a bit of a characterization out of history. So back when people were first making up these definitions, they didn't know that it was a temperature sequence. It was originally just based on what you're seeing in the stellar spectrum and classifying them based on the strength of the hydrogen lines. And it wasn't until later that we got them in this nice order. And so for a lot of these historical reasons, the M-dwarf category maybe isn't how you would characterize stars if you were designing a characterization system from scratch today based on everything we know about stars. So these are M-dwarf spectra. Here they have all sorts of different lines in them. That's because they're so cool. So you have all these condensed molecules in the atmosphere. So the other thing that you need to know about M-dwarfs, one of, I guess, many things you should know, is that they're the majority of all stars. If our universe was 100 dwarf stars, M-dwarfs would be 75%. So again, if we were making a system today, you probably wouldn't lump 75% of all things into the same category, but that's the hand that we are dealt from history. And you see that nicely in this illustration here, that they're the most abundant, but they're certainly not the most light. If you looked up at the night sky, you're not seeing any M-dwarfs by eye. They're really faint. But what this illustration doesn't convey, all the M-dwarfs shown here look like they're the exact same, but they're not. M-dwarfs are a really diverse category. And so this plot better illustrates that fact. We're looking at the distribution of stars in our solar neighborhood as a function of mass. So our sun is here at 1 on our x-axis. And again, you see that M-dwarfs are the most abundant. They're 75%, this red part of the histogram. But what you'll also see is that they're spanning a huge range of the x-axis, right? Nearly an order of magnitude in stellar mass, from about 8% the mass of the sun up to about 60%. And so if we were going to, come up with a different classification system for stars that is maybe a bit more physically motivated, we might want to split up this really large bin of very diverse properties in a bit of a different way. And so one place that you might logically think to do that is a physical transition that happens smack dab in the middle of our M-dwarf category, which is the fully convective boundary. So stars that are more massive than this are structurally very different from, or very similar to the sun. You've got your radiative core and you've got your convective outer envelope. Well, to the right of this line, you no longer have a radiative core. The core has got smaller and smaller as you've moved right on this diagram, and by the time you get to this boundary, you have a fully convective star. And so that means that early M-dwarfs and later type M-dwarfs are fundamentally very different in their stellar structure, in their energy transport, in perhaps their magnetic field generation. And so these are all things that we want to account for when we're talking about M-dwarfs. They're not a monolith. They have all this diversity in them. And so something else, I guess, to keep in mind when we're talking about M-dwarfs as a category is, there's some arbitrary distinctions here. And if you're thinking about, is there some fundamental difference between the very latest K-dwarf and the very earliest M-dwarf? Does it mean something special to be an M-dwarf? The answer really is no. It's the smooth continuum as we go as a function of mass and temperature. So that's our M-dwarf population. I'll talk throughout this talk a lot about early M-dwarfs and mid to late M-dwarfs, and you can think about that fully convective boundary as kind of a dividing line between these two populations. For the people in this room, perhaps the most important part for M-dwarfs is the fact that they're really useful for studying planets. And the reason for this is because they are so small. So we saw on the previous slide that the distribution ticks up as we go to lower masses. So most stars are not just M dwarfs, but they're specifically these very small mid to late M dwarfs. And if you put a planet transiting in front of a sun-like star, it's blocking out a little bit of the starlight, and you're going to get this little transit dip here on the bottom left. But if you put that same planet around an M dwarf, well, now that same planet is blocking a larger fraction of the starlight, and so you get a larger dip. And this is for an early M dwarf, but if you play the same game for a mid to late M dwarf, the dip gets really big because, again, it's a smaller star, you're blocking out a larger fraction of the light. And it's actually a bigger difference between the mid to late M dwarf and the early M dwarf than it is between the early M dwarf and the sun-like star. So when we think about M dwarfs as being advantageous for the detection of planets, really we get the most bang for our buck as we go to the very smallest M dwarfs. This is for transits, but the same thing applies for radial velocities. Smaller star means a bigger wobble due to the tug of that planet. And also not just for detection methods. The same thing applies for ways that we characterize planets. Like transmission spectroscopy, where we're looking at the atmosphere of a planet based on seeing how the radius of the planet, the transit depth, is changing in different wavelengths of light. So again, as we have a smaller star where we get better sensitivity to these small changes in transit depth, we're able to better characterize planets using this method. And then we think about this overarching question that we have within the field of hoping to be able to characterize the atmosphere of a terrestrial planet, or a terrestrial exoplanet rather. Not just a sub-Neptune or a giant planet, but specifically a small rocky body. We're only going to be able to do that with JWST around these very smallest stars, assuming that their planets do in fact have atmospheres. And we'll come back to that idea towards the end of the talk. But M dwarfs are just very exciting because they give us access of the best sensitivity for all our different planet detection and characterization techniques. The one final thing to highlight about what makes M dwarfs special is the fact that because they're so faint, their habitable zone is so much closer to their star than it is for sun-like stars. So TRAPPIST-1 is our favorite late type M dwarf, or at least my favorite late type M dwarf. You can make your own decision. But this is a system with a series of small rocky planets, some of which are in the habitable zone of their star. But when you compare that to our solar system, all those planets, habitable zone or not, are well within the orbit of Mercury if they were in our solar system. But because TRAPPIST-1 is so faint, that means that the habitable zone is really close to the star. And so this entire system is working on a much smaller length scale than our solar system would be. Which means that if we're trying to detect and characterize planets in the habitable zone, small M dwarfs have a really big advantage because they mean that we don't have to look for as long amounts of time in order to detect transiting planets. The habitable zone planets have a higher probability of transiting. So we don't have to look out for a whole year in order to see a planet that's in the habitable zone like our Earth is. So that's kind of our crash course on M dwarfs and why you all should care about them. And with that, let's move on to talking a bit about demographics. So our journey in M dwarf demographics starts in the Kepler era. And Kepler was not a mission designed to work on M dwarfs. And in a couple of slides, we'll come back to exactly what that means. But first of all, what we should say is that despite not being meant for M dwarfs, Kepler was still able to do some really good statistics, and especially people like Courtney produced this result here, which is the occurrence rate of small planets coming out of Kepler. So this is a plot of the cumulative planets per star as a function of period, with the different colors being different radius bins for the planets. And the main result here is just pulled from the conclusion of that paper, that for orbital periods shorter than 200 days, small planets with radii of 1 to 4 Earth radii, so these are the super Earths and sub-Neptunes, have a cumulative planet occurrence rate of 2.5 planets per M dwarf. So these things are exceptionally common around M dwarfs. On average, every M dwarf has multiple small planets. One thing, though, to keep in mind with the statistic is that we're really talking about early M dwarfs here. So the median host mass in the sample is 0.5 solar masses, so firmly in that early M dwarf regime. So if we want to think about later type M dwarfs, we need to go to a different survey, and that brings us into the TESS era. As I mentioned, Kepler was not meant to look at M dwarfs, but TESS was. And you can kind of see that when we look at some of the different specifications for the different telescopes. So I'll draw your attention specifically to this lower right plot, which is showing the band passes of Kepler and TESS. So a G dwarf, like the sun, has a spectrum that's this blue line here. And M dwarf has a spectrum that's going pretty much the opposite direction, like that. So a G dwarf emits most of its light at bluer wavelengths, and an M dwarf emits most of its flux at redder wavelengths. And so Kepler's bandpass, the wavelengths that Kepler was able to detect, was focused to catch all this light coming out of the G dwarf. Well, TESS's bandpass is shifted much more to the right, so it's able to catch where those M dwarf spectra peak and those redder wavelengths where M dwarfs are emitting a lot of flux. So it's a mission that's focused to get at these M dwarfs and also to get at nearby stars in general because it's an all-sky survey. So while Kepler was focused on one patch of the sky, TESS is doing all of it. And so this upper plot is showing TESS sky coverage as of sector 94, which is the sector that's currently being observed right now with TESS. And you see that 98.6% of the sky has currently been covered with at least one sector of TESS data. So everything except for that one little patch. So basically, every single nearby star has a TESS light curve, although it's limited by the fact that they only have 27-day sectors in TESS. So you're not able to get these nice like 200-day periods for most TESS targets. You're limited to closer in planets. But with our mid to late M dwarfs, we have the advantage that the habitable zone is well within that shorter period regime. So the statistics we're able to do are still quite good. So if we ask the question of, what did TESS see? What occurrence rate constraints come out of the TESS survey? We can look at this work from Menton Charbonneau in 2023, which looked at a volume complete sample of every nearby mid to late M dwarf out to 15 parsecs that had been observed in TESS by that time. So we've seen a lot of plots like this so far this week. These are the completeness contours coming out of their survey. So they inject fake planets into their data and recover them to see how to correct for the completeness of their investigation. And that turns into this occurrence rate distribution. So specifically, they find that their detections are consistent with a nice Gaussian centered at a radius that's a little bit over the radius of the Earth and dropping down on both sides. So it's kind of like the radius distribution, but it only has one peak and not two. There's no sub-Neptunes. And that's what they found. They didn't detect any sub-Neptunes in the survey, despite having greater sensitivity to sub-Neptunes than they do to smaller planets. So it's a really different distribution than what was seen for Kepler for the earlier M dwarfs. And so this is a table kind of highlighting the differences between those two results, specifically focusing on insolations greater than 4 times the flux received by the Earth. So we're talking about the inner parts of the solar system because TESS doesn't necessarily give us good statistical access to longer periods, unlike Kepler. But if we compare apples to apples, those two surveys over that inner portion of the solar systems or the stellar systems, this is what we find. That for rocky planets with radii less than 1.5 Earth radii, for the early M dwarfs, the occurrence rate is about 0.5. So there's one of these planets for every 2 stars. And for mid to late M dwarfs, it's about the same, 0.5, so 1 and 2. But for the sub-Neptunes, things change dramatically. Because for the early M dwarfs, it's about a 1-to-1 ratio of rocky planets to sub-Neptunes. There's an equal number of both. And for the mid to late M dwarfs, there's none. They didn't find any sub-Neptunes, which lets them put an upper limit of about 6% on their occurrence in these inner parts of the orbits. So that's a ratio of at least 13-to-1 in favor of rocky planets. So there's a big difference when we're thinking about early M dwarfs and mid to late M dwarfs in the types of planets that they have in their inner solar systems. We can go up in mass further and think about giant planets. You would have seen this plot yesterday in Ilaria's talk, so I'll just quickly recap that. This is giant planet occurrence rate out to 10 days. So we're talking about hot Jupiters. For sun-like stars, you're up here around 0.6%. And then as you go to early M dwarfs, it drops off to about 0.3. And for mid to late M dwarfs, drops further to around 0.1. So hot Jupiters are rare for early M dwarfs, and they're even rare for late Ms, which is something that we predict coming out of planet formation theories, that the core accretion framework predicts it's harder to make these big planets around small stars. But if you remember from this morning, hot Jupiters are a very small fraction of the giant planet population. So what we really want to know is, what about cold giant planets? And TESS isn't great for that because of the limited 27-day sectors, but we also have radial velocities. And so this is a study that uses the same volume complete sample of nearby mid to late M dwarfs from that mentioned Charbonneau paper. But instead of looking at TESS data, we looked at radial velocities that we monitored over the course of a few years. And so this is 200 stars, and out of them, we didn't find any giant planets, despite having quite good sensitivity. So these are the 95% confidence upper limits that we can place on the occurrence rate of such planets. And the white line there is the snow line. So you can put pretty tight limits even out beyond the snow line where these cold Jupiters would exist, that they're really rare around mid to late M dwarfs. So when you put these two facts together, that terrestrial planets are common and giant planets are rare, that means that M dwarfs do not have planetary system architectures like our own solar system. Instead, you probably have systems that are more similar to the TRAPPIST system, where you have a lot of small rocky planets and no giants, no bigger things there. This is in contrast to what's happening for sun-like stars, where demographics work has shown that it's decently common to find inner small planets in systems with outer Jovians. So these M-dwarf planet systems are distinct from both our own solar system and other sun-like systems out there. And so we can think about what that means for these planetary systems orbiting M-dwarfs. What does it mean to only have small planets and not having cold Jovians? So this is a plot from Alessandro Morbidelli showing the evolution of our early solar system, a model of that, accounting for the migration of Jupiter and Saturn. And essentially, because Jupiter is so massive, it had a huge dynamical influence on the early solar system, controlling the flow of icy material and dynamically sculpting that inner solar system, exciting the asteroid belt. So you can imagine how without Jovians, you might have a very different composition and water inventory for the inner solar system and those inner small planets. So that brings me kind of to this overarching category of thinking about demographics beyond occurrence rates. We can think about architectures, we can think about compositions. What are these planets made of? And there's so many things that we can talk about within this category, but I'm just going to touch quickly on two ideas. The first being, we see when we look at these compositions, when we have precise masses and radii, that a lot of the small planets are consistent with just being rock and iron, as we might expect based on more massive stars and also based on planet formation theories. So a good example of that is our favorite TRAPPIST-1 system. So this is results from Eagle et al., who used the transit timing variation method to get masses for all the TRAPPIST-1 planets. And what they found, this is a mass radius distribution. So all the planets are shown there, and the lines are showing different composition models. And what they found is that all 7 planets' densities can be described with a single rocky mass relation, which is depleted in iron relative to Earth by a little bit. So all the planets in the system are consistent with being made out of the same stuff. So the rocky side of the radius valley for these low mass M dwarfs, many of them seem to be consistent with these pure rock compositions. And we've heard a lot earlier today about subneptunes. And there's a lot, obviously, to say about all the work that's been done to think about what subneptunes are made of. Are they water worlds? Are they enveloped terrestrials? But one interesting thing that M-dwarfs can do for us is help us test some of these theories based on looking at the slope of the radius valley. So I was a little worried that this might be quite busy for a signal slide, but fortunately, you got a great introduction to this idea both earlier today and yesterday with Ilaria's talk. So when we're talking about the slope of the radius valley, what we're talking about is, you have this radius valley in the histogram of planetary sizes. So it's the dip between the super Earths and the subneptunes. And then the slope of the radius valley is plotting the position of that valley as a function of period. So mapping out an additional dimension. And for sun-like stars, it follows this downward slope, as we heard about this morning. But it doesn't do that for M-dwarf planets. For M-dwarfs, it follows this flat line, the solid line here, where it doesn't depend on period. And so that therefore has implications for atmospheric mass loss and planet formation theories, as we heard about in BJ's talk this morning. I'll also note that this is coming from Kepler and K2. So these are specifically results for early M dwarfs again. As we heard about, subneptunes are a lot rarer around our mid to late M dwarfs. So other types of demographics that we can think about is atmospheres. I mentioned this at the beginning of the talk, that it's really exciting thinking about terrestrial planet atmospheres around these mid to late M dwarfs, because that's where we're able to detect them with JWST if they were to exist. And this is something that is happening right now. Some of you may have heard of this Rocky Worlds DDT program. So it's a director's discretionary program with JWST that has 500 hours of time specifically to answer this question of whether M dwarf terrestrial planets have atmospheres. And it might be that these planets don't have atmospheres, but this project is archival legacy survey in order to answer that question, similar to how the Hubble Deep Field was a legacy survey that was meant to bring about a lot of exciting new science. So why might these terrestrial M dwarf planets not have atmospheres? Well, of course, stellar activity can strip planetary atmospheres. And as we've already heard today, M dwarfs are active for a really long time. Putting some numbers on it, if we have a mid M dwarf, it remains in the saturated phase of its X-ray and UV activity for a little over 1 billion years. But it's really mass dependent, so that by the time we get down to a 0.1 solar mass M dwarf, it spends over 4 billion years in that phase. So it might be that these poor planets orbiting those stars, they're bombarded by this high energy environment for such a long time that it's just hopeless for them to retain their atmospheres. So can we put, we have this question of, are all M dwarf planets bare rocks? And that's what JWST is going to try to answer with this program. What that would look like if they are bare rocks, a good example is coming from Laura Kreiber's work on LHS 3844b, which is a close-in M dwarf planet that she observed with Spitzer. And just to recap what you're seeing when you're looking at a phase curve or you're looking at emission, your planet is orbiting around your star, and when it passes in front, it transits, and when it passes in behind, it eclipses. But the key part here is that when it's transiting, just before it transits, the face of the planet that you're seeing is the one that's not being irradiated by the star. So you're seeing the night side of the planet. And at the moment before it eclipses, you're seeing the side of the planet that's irradiated by the star. So you're seeing the day side. So to annotate Laura's plot, up here you're seeing the hot day side of the planet, and down here you're seeing the cold night side. And the fact that there's a big difference between these two sides is telling you that you have poor heat redistribution. And that implies that there's not an atmosphere on this planet, because that would spread around the heat and cause the sides to have a similar temperature. So the question is JWST going to see something like this for all the M dwarf planets? And if we want to try to put some numbers on it before that data comes down, we can think about it in terms of this cosmic shoreline paradigm, which is an idea coined by Zanley and Catling in this 2017 paper. So what they did is that they looked at bodies in our solar system, so all the planets, all the asteroids and moons, and they plotted them on this diagram of the total XUV flux that that body has received over its entire lifetime as a function of the escape velocity off that body. And when they do that, and then they add this line shown in green, which is the XUV proportional to the escape velocity to the power of 4, they find that that line nicely subdivides our solar system into 2 halves. Above that line, you have the bodies that don't have atmospheres. And below the line, you have bodies that do have atmospheres. So it's this idea that this green line, this cosmic shoreline, is a prediction of a body's ability to retain an atmosphere in the face of escape processes. And so it makes a prediction for all those exoplanets that are plotted on the top of the plot, which ones would have been able to maintain atmospheres within this paradigm. If we put all the mid to late M dwarf planets that we know about on a plot like this, it doesn't necessarily look too promising. They have this really long-lived XUV flux, so a lot of them are really high up on this plot above the nominal shoreline. So our prediction might be that it's really tough for these planets to retain atmospheres. But this cosmic shoreline paradigm is a really simple picture of escape, and it's just a scaling based on our own solar system. So ultimately, it may be that it's more complicated than this, and some of those planets will end up having atmospheres. That's what's exciting with the JWST program. It's going to put this to the test and see where that cosmic shoreline truly falls for M-dwarf planets. The yellow squares are showing the 4 targets that have already been selected for this project. It's a community project where people can contribute ideas, and they're going to finalize, I think, the full target list later this year in the fall. So more targets will also be part of the program as well. So I'm really excited, especially, of course, about this one that's below the nominal shoreline, what they're going to find about M-dwarf atmospheres. Great. So just to conclude, a summary of what we talked about today. There's a big difference between early and late M-dwarfs. And when we're thinking about an early M-dwarf, arguably it's more similar to the sun than it is to a star like TRAPPIST-1. And so when we talk about M-dwarf planetary demographics, we need to account for these differences, and all M-dwarfs are not the same. Small planets are abundant for all types of M-dwarfs. On average, there's more than 1 per star. But when we think about the difference between early and late M-dwarfs, there's perhaps a big difference in those populations, where they have similar numbers of rocky planets on short orbits, but late M-dwarfs have far fewer sub-Neptunes. Giant planets are really rare across the board, getting rarer as you go to smaller host masses. And then there's this question of whether these rocky M-dwarf worlds have atmospheres. And that's kind of an exciting question that will be answered probably in the next coming years. So that's all I wanted to share. I'm happy to take any questions if you have them.
Thank you. Right. There is a ton of discussion online, which is fantastic. So this is a reminder to all the speakers for today to check the Thursday Talks channel. I'll kick things off with an online question, and then we probably have time for one question in the room before the panel. So this online question is from Puneet Sethi, which is, there's so many interesting questions. Given the deeper transit of M-dwarfs, is there any practical limit where stellar variability starts to counteract the benefit of deeper transit depths?
That's a great question. And it certainly depends on the type of star. So for M-dwarfs that are active for a long time while they're younger, activity is going to be playing a much larger role than when they're younger and more quiescent. So when you look at, for example, test data of really young M-dwarfs, you see huge spot modulation patterns that are dramatically larger than the transit depth in a lot of these small planet cases. But it's kind of a coherent pattern. So there's ways to correct out that modulation and still get at the transit. So I wouldn't say that there's a hard and fast rule of, this is a certain mass where you're no longer able to do this, but it certainly does get more challenging and computationally difficult to account for how activity affects things. For transits, it's probably less significant. For radial velocities, it becomes hugely important, and it's really difficult to get good radial velocities for active M-dwarfs.
Answer. Thank you. Dr. Beischman.
Initial atmosphere due to the activity of the star. What happens to any secondary atmosphere that they may also create now and presumably the more quiescent phase of their host stars?
That's a great question. And it really depends on, when is that atmosphere being outgassed? Because I showed those numbers up here on the slide. And there's a lot of, times you could think about an outgassed atmosphere happening well before 4 billion years. So that atmosphere is outgassed and the star is still very XUV active, and it's still going to likely suffer these escape processes. But there's different modeling work that shows, you can have water in the mantle that's outgassed later, and that can lead to water-rich atmospheres later in the life after the XUV activity has died down. I'm thinking of Moore and Cohen 2020 is one of those modeling papers. So it really depends on specifically in your model when that atmosphere is getting outgassed and what type of star that you have. So when that XUV is calming down. And then there's also the flare question as came up earlier today, that even after this long-lived XUV saturated phase dies down, you do still have the problem of flares.
Okay, we'll do one last question, but the panelists can go ahead and come on up. Go ahead.
Thank you. Thank you for the talk. Just wanted to know, what is the impact of tidal locking on any potential exoplanet around an M-dwarf star on their atmosphere? Thank you.
Yeah, that's a great question. So for these mid to late M-dwarfs, like for all the TRAPPIST-1 planets, for example, they're all likely tidally locked. So you're going to have well, when you think about this idea of, tidal heat redistribution, for example, you're always going to have the same face of the star being irradiated. So you basically more complicated modeling is required to really understand those effects, but that's certainly something that needs to be accounted for when you're thinking about escape processes, that it's going to be the same part of the planet being irradiated. And that is probably for all these mid to late M dwarf planets going to be a factor, that tidal locking.
Great. Thank you very much. Let's thank Dr. Pass and all of our morning speakers again.